Okay, today we're going to be investigating where the mole comes from and what exactly the relative mass is. We've talked about the fact that the mass is recorded on the periodic table and the atomic mass unit is a mass unit that is defined in terms of the carbon-12 isotope, and the mole is actually defined in a similar way. You'll notice a mention of the carbon-12 isotope in the mole definition. So we're going to look at how exactly do we count particles without actually counting them. Again, atoms are way too tiny for us to count. There's way too many of them for us to count. And so this method of using the mole to help us count things is what scientists came up with as a solution to the problem of how do you count an atom without actually counting them. So we're going to take samples of beans. I have equal numbers of beans in each of these cups. So I've got white beans, black beans, lentil beans, and brown beans, as you can see from your worksheet. And I'm going to be measuring the masses of each of these bean types. And again, similar to what scientists did in defining the mole, they took equal amounts of atoms. How exactly they figured out that they had equal amounts, that's a topic for another day, but they took equal amounts of atoms, and then they did something similar to what we're about to do. Okay, so here's the white beans. And again, in the mass column, we're going to write 19.26 grams, and that's for the white. Make sure my balance goes back to 0 every time. And the black bean, we've got 19.80. For the lentil bean, 4.96 grams. 4.96 grams. And then lastly, for the brown beans, we've got 41.57 grams. Okay, so those are the masses of, again, equal numbers of beans. I'm not going to tell you how many beans they are because, similar to atoms, that was a difficult question to answer. How many atoms are there exactly? Well, we don't know, but we can figure out if we've got equal numbers of atoms, whatever that number might be. So next thing we're going to do is find what's called a relative mass. Now, again, the real relative masses on the periodic table are relative to the carbon-12 isotope. And so we're going to pick something to make our masses relative to, and we're going to pick the lentil bean. So that one has the smallest mass. So again, the reason we're doing that is because of what it says in our directions to pick the one with the smallest mass. So we're picking lentil bean, so that's 4.96 grams is its mass. So to find a relative mass for the other bean types, we're going to divide each of the masses of the other bean types by the lentil bean mass. So we're going to take the 19.26, so you do this on your calculators, divided by 4.96, and we're going to keep three significant figures because the 4.96 has 3 digits. That's going to limit us to 3. So when I divide 19.26 by 4.96, I get 3.88. So if you notice there, I'm filling in my chart, and so you should go across and do the same thing. So 19.8 divided by 4.96. So what these numbers give us are the masses of each bean type relative to the lentil bean. So what that means is I'm kind of comparing, again, even though I don't know the mass of the individual beans, what these relative masses tell me is, well, compared to the lentil bean, the white beans and the black beans are around 4 times the size of the lentil bean, and the brown bean is about 8.4 times the mass of the lentil bean. The brown bean is, a little bit more than twice the mass of the white bean and the black bean. So even though we don't know what the individual masses are for the beans, we do know what the masses are relative to one another. Again, this is because we had equal numbers of beans in each of our samples. Okay, so now we're going to put our weigh boat back on, and we're going to try to measure out. So these relative masses, I want to see, well, how many beans are in the relative mass of the white bean? So I'm going to try to get 3.88 on the balance, and I'm going to count how many beans it takes to get there. So that's what we're filling in the last part of the table. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That gets us pretty close. So probably if we put one more bean on, we would go over. So 20 beans, we will write down the number of beans and the relative mass for the white beans. Okay, we're going to go down the line and do this, measure out the relative masses for everything else. Okay, so we've got the black beans, looking for 3.99 grams. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 4.05. So that's probably about as close as we're going to get. Let's see, if I took one away, that would take us way too low. Okay, so we're the closest with 20 beans for the black. Right, and lentil, same thing. So this will be 1 gram for the lentil. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That is almost to the 1 gram we want. Let's see, adding one more. There we go. Okay, so that's 20 beans. 20 beans of the lentil. And then lastly, for the brown, you can kind of see where we're going with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and let's see here, we want to get to 8.38, 21, take one away, back to 20, there we go, that's pretty close, 8.38 is what we're shooting for, 8.32 is pretty close, as close as we're going to get, so that was 20 brown beans as well. Okay, so notice that the number of beans in our relative mass for each item, for each bean type, actually ends up being the same number. And so this is similar to what was done with the definition of the mole. So when we look at the definition of the mole, it's defined as the number of atoms in exactly 12 grams of carbon-12. Well, in our definition of we're going to come up with a definition here called the bunch. We're going to call the bunch the number of beans in exactly 1 gram of the lentil bean relative mass, which is 1 gram, and as it turns out, that number is 20. Because we are working with our relative masses, again, it doesn't matter how many beans we have, as long as they're the same, as long as we're comparing the same number of white beans to black beans to lentil beans to brown beans, that ratio of their masses is always going to be the same. And so that's what we find with the mole. So when we're looking at the periodic table and we look at the definition of the mole, which is defined in terms of carbon-12, well, because all of those masses on the periodic table were found similarly, where they're relative to the carbon-12 mass, what we know is that, if I have, well, if I look at the mass of hydrogen, for example, it is like 1/12 the mass of carbon. Or if I look at magnesium, it's about twice the mass of carbon, because magnesium is around 24.3, carbon is around 12. So if I have 10 atoms of magnesium and 10 atoms of carbon, we're going to have that same mass ratio comparison. If I have 100 magnesium atoms versus 100 carbon atoms, we're going to have that same mass ratio. And if I were to have some gigantic number, like let's say 6.02 times 10 to the 23rd atoms of magnesium, as long as I'm comparing it to 6.02 times 10 to the 23rd atoms of carbon, there will be the same mass ratio. And so that is where we get our mole concept from, and the definition of molar mass, which is the mass of any element. 1 mole of atoms of any element is the relative mass from the periodic table in grams. And so we'll stop here. You can fill in the rest of your worksheet, but I kind of went over the missing pieces. But again, this is where we're going with the mole, and this is kind of the idea behind how the mole was defined in the first place.